Hello, everybody, and welcome to our presentation today. My name is Andreas and together with Dominik we are talking about excavation and conveying of lunar regolith on the moon today. Let's have a look on the table of content. We will start with a short introduction of ourselves. Who are we and in which scientific field we are located. Afterwards, Dominik will tell you something about the NASA challenge and how we got in touch with this topic. After that, he will summarize the main properties of lunar regolith. I will continue with the ISRO chain and what are the crucial steps of the ISRO chain. And at the end, Dominik will talk about the excavation concepts for the for the moon and will present his design approach. And at the end, I will talk about conveying on the moon, and I will also present my design approach of the conveyor. Yeah, as I mentioned before, and Gisela mentioned, I'm Andreas Daschner. I'm a mechanical engineering student in the master's program at the Montanuniversität Leoben in Austria.
Yeah, thank you, Andreas. Hello, everybody. My name is Dominik and I'm also a master student in mechanical engineering at the Montanuniversität Leoben. For us, it all started when a challenge was announced by the NASA. It was the NASA Bucket Drum Design Challenge. Together with another student and our supervisor, Eric, we designed a concept drum for the prototype of the NASA Resor. The Resor is the regolith Advanced Surface Systems Operations robot, and it's a robot which should be used on the moon to mine and to transport regolith. We are proud that the jury decided to honor our submission out of 350 entries with the fourth place. After this challenge, we wanted to take a closer look to space mining, and so we got hands from Professor Sifferlinger and his team to write a master thesis about this topic. While I am dealing with an excavation or mining unit, Andreas' thesis is about an associated conveyor unit. First of all, let's start with the lunar regolith. Regolith is the material, or lunar regolith is the material which covers the whole surface of the moon, which with a layer thickness of 4 to 50 meters. This regolith was formed through meteorite impacts. When a meteorite hits the moon, it was broken down into millions of pieces and then got distributed over the whole surface. In the picture, you can see a regolith agglutinate. Agglutinate is a mixture of regolith and glass. This agglutinate was created through the high temperature at the collision from the meteorite with the moon. Regolith is important because it consists of many different materials which are bound as oxides. As you can see in this picture, this agglutinate has a very sharp grain form, and this grain form can be a problem for machines because of the increasing of the wear. In the table below, you can see the cohesion, the internal friction angle, and the bulk density depending on the depth. And you can see that the cohesion is very high, and that can be positive or negative to some functional principles.
Yeah, let's have a look on the ISRO chain. First of all, ISRO means in situ resource utilization. Basically, the long-term goal is to be independent of the Earth. This means that there are no products, goods, or other consumables are transported from the Earth to the moon. Yeah, in the early stage of the ISRO chain, or the ISRO chain should focus in the early stage on oxygen production to enable longer human exploration missions and refuel rockets from our point of view. Here in the figure, you can see the four main steps of the chain. Yeah, the first and initial step is the excavation step. Yeah, in this stage of research, often excavators are developed or under development, which are excavating the uppermost centimeters of the lunar surface, because underground mining would be really difficult because there are no information available of the subsurface properties. After the material is excavated, it has to be conveyed. The excavation site is usually a few hundred meters away of the production plant, because during the excavation process, much dust is generated, and this could lead to disturbances in energy production with solar panels. When the material reaches the production plant, a beneficiation or separation step is necessary to reach a certain degree of material enrichment. Most terrestrial applications use gravity or fluid-based technologies, but these technologies won't work on the moon since the gravity is low compared to the Earth, and there are no fluids available on the moon. And the last and probably most crucial step is the processing step, where the feedstock material is converted into oxygen. There are already some technologies developed, such as the hydrogen reduction or carbothermal reduction. All these four steps has to work and interact completely autonomous, so that no human on the moon is necessary. So yeah, when it comes to, but there will be some challenges and problems when it comes to developing an excavation and conveying unit for lunar applications. First, yeah, the most terrestrial machines or machines for the Earth are heavyweight solutions, but this would be very problematic since, yeah, a heavy payload isn't transportable to the moon or really costly. But most excavating machines have a high own mass, which is leading to a high excavation force. But this principle won't work on the moon since the gravity is really low. So for example, when a machine wants to dig material, it pushes itself away instead of digging the material. So what's more, the powdery condition of lunar regolith leads to a soft surface. Robots and units are often based on wheels or chains, and they will sink a few centimeters into the surface, and this will lead to a higher energy consumption when they are driving. As Dominik mentioned before, regolith has some unique material properties. High cohesion is especially a problem for conveying machines. For example, they often clog transfer points. And in general, regolith is really abrasive and has a sharp grain shape, which causes high friction and wear. And this is problematic for mechanical and moving parts. The day and night cycle is completely different as this on the Earth. 14 days of sunshine are followed by 14 days of night. This would be problematic for the energy production with solar panels, and the high temperature fluctuations are problematic for electrical devices like control systems. And lastly, maintenance wouldn't be available on the moon. This is a huge restriction. So that means that there is no human on the moon which repair our machines. And now Dominik will talk about his design concept.
Yeah, first of all, there are many different possibilities of mining concepts which may work on the moon, like backloader you can see in the first picture, a scrapper, a front loader, a bucket wheel, like these other two pictures, or a bucket drum, like the NASA Razor. It is also possible to use flexible auger systems, impeller systems, pneumatic systems, and bucket ladder systems. I have taken a closer look at all of these principles, and in the end, a bucket ladder was the most promising concept for me, because a bucket ladder has more buckets, and more buckets decrease the wear of every single bucket. And it's also possible to have a larger degradation area onto leveling the surface for moon bases or launch stations for rockets. So my concept was the use of a bucket ladder connected with a bridge. You can see it on the picture. On both sides there is a robot and the horizontal bucket ladder. The main advantage is that we use scrapping instead of digging. That's better because of this low gravity. The two outer segments can be varied in position, so it's possible to adjust the angle and also regulate the mining depth of this excavator. With this concept, it is possible to mine with semicircular degradation areas and with rectangular degradation areas. While the semicircular degradation, one robot stands still and the other one drives a semicircle around it. And at the rectangular degradation, both robots drive in the same direction. I've also done optimization of the shovel shape, but this wouldn't be a part of this presentation today. Another important point is the discharge. Bucket elevators on Earth normally use gravitational and centrifugal discharge. But, this discharge simulation has shown that these principles won't work for my concept. So there was the idea of using a notching mechanism. So the bucket, as you can see in the picture, swings out while moving vertically upwards. I've simulated this process, and you can see in the picture below the use of a stop block. When the bucket hits the stop block, an impulse increases the discharge speed. You can see in the picture with the stop block, this is a few moments before hitting the stop block, and the other picture is a few moments after hitting the stop block. You can see that these blue particles, which have a velocity near to zero before hitting the stop block, have, after hitting the stop block, a velocity of at least 1.50 meters per second, and so the discharge time is shorter. It is also necessary to fix this bucket after hitting the stop block to avoid a rebound. Here you can see my final bucket design with many different functions, like the hooks to lock the bucket, and at the end of this connection plate there is the stop block. Here you can see now my final design. On the left side, you can see that there are 17 buckets used in the system. On the left side, there is the smaller robot with the clamping station. This clamping station is an important part for the whole system because it regulates the pre-tension of the rope during the dismantling and also during the adjustment. On the right side, there is the main robot with the dispatch station and the chute to transport the material from the excavator to the conveyor. The conveying unit is positioned at the end of the main robot. In this slide, there are the two end positions of this concept. So on the left side, there is the maximum distance from the buckets to the surface, for instance, while driving. And on the right side, there's the maximum excavation depth. A higher variation angle isn't reachable without higher technical effort, and it wouldn't be any advantage. This maximum excavation depth is more than enough because simulations have shown that the excavation depth will be between 25 and 40 millimeters.
Yeah, let's move on to the different conveying concepts. Based on the problems I mentioned before, I investigated roughly 10 to 15 different conveying concepts and thought about implementing them for lunar applications. And now I will talk about 3 of them. First one is the electromagnetic conveyor. In this picture, you can see one proposal. It's the lunar soil magnetic collector. The most essential part of this conveyor are the wound coils. The coils are controlled individually to generate magnetic fields in sequence. So powering down the coil before and powering up the next coil leads to the transportation of the material along the conveyor. The main advantages of this concept is that there would be no or minor dust development because the material is conveyed within a pipe, and there will be no friction between the conveyed material and the conveyor itself, and there are no moving parts which could be get disturbed by the lunar dust. But there is a huge disadvantage of this conveyor. Not all portions of lunar regolith are conveyable, meaning that not all portions are magnetic. The second one is the pneumatic conveyor. The pneumatic conveyor is a well-known solution on Earth, and a pneumatic conveyor for short conveying distances up to a few meters are already under development by NASA, but not for longer conveying distances, such as a few hundred meters. This system has almost the same advantages as the electromagnetic conveyor, but the realization of such a conveyor would be really difficult, and it would be really complex to avoid leaks of the system. And the last one is the ballistic conveyor. This technology was already in use in the Middle Age to throw stones on opponents. Although the ballistic conveyor is not often used in terrestrial applications, there are several crucial advantages for this system and for the use of this system on the moon. First of all, the gravity is only 1/6 compared to the Earth, and there will be no air resistance, which results in a longer conveying distance. And it would be possible with this system to overcome obstacles and barriers. So for example, you can transport the material from the ground of a crater to the lunar surface. And as I mentioned within the problems, the material is very cohesive, which is usually a problem for conveying system, but in this case it's beneficial for the flight behavior of the thrown material. And lastly, the conveyor has a low own mass compared to the conveying distance, and it is also a dynamic or mobile system is feasible. So this concept has the most advantages and most crucial ones, so I focused on this technology. Initially, I distinguished between 2 basic principles, the ballista and the catapult. The ballista accelerates linear, while the catapult accelerates rotationally. And at the ballista, it is easier to adjust the throwing angle and to adjust the throwing direction. So I decided to develop a conveying unit based on the ballista principles. In the next two pictures, you can see my design approach for the conveying system. The major assembly are the two big gray pipes with the yellow bucket. Within the gray pipes, there would be a drive. The drive accelerates the yellow bucket, and after a certain acceleration distance, the bucket is slowed down by a damper, and the material is released and flies to the certain, to the desired location. The other main assembly of the system is the distribution system. The distribution system consists of a rotating ground plate and 3 robots which are mounted on top of the ground plate. The ground plate rotates continuously, and it's a working principle of a closed loop. There are 4 main steps shown in the right picture. Starting in the left top corner, the red bucket, hopefully you can see it, the red bucket is filled and is transferred to the throwing machine, while the blue bucket is refilled. In the second step, the red bucket is in the throwing process and the green bucket is in the refilling process. And the blue bucket is already refilled. After that, so in the third step, the red bucket comes back from the throwing process and the blue one is near to the changing point. And in the last step, the blue bucket is transferred to the throwing machine and the red one goes back to the filling station. And finally, the process begins again. In the next animation, you can see how the process would work.
Okay, let's summarize our presentation. So the main goal is a fully functional ISRA chain for the oxygen production. The excavation, or the main advantages of this excavation concept are the scrapping instead of digging, the possibility of leveling the surface for further use, and a large degradation area. The advantages of the conveying unit, of the ballistic conveying unit: large conveying distances, obstacles are recoverable, and a low own mass related to the conveying distance. Now that a combination of these two machines or units, only one driving unit for 2 steps of the ISRA chain, and a completely collaborating machine. With this system, it is possible to convey or to excavate 1.2 cubic decimeters per second. For example, for one rocket launch, or for the production of enough fuel for one rocket launch, you need about 330 cubic meters. With our volume flow, it will be possible to produce enough oxygen for 3 rocket launches in 2 lunar days, which are about 2 months on the Earth. So we are now at the end of our presentation. Thank you for your attention, and we are looking forward to your questions.